whatever you call me by, and we're here with Unit 3 of Chemistry. Woo! Um, so yeah, this unit is all about energy, so I guess let's get into it. So what is energy in the first place? Well, energy, the definition of energy is the ability or capacity to be able to do work, right? You need energy to be able to do anything, right? So what are the different types of energy, right? So we have potential energy, which is energy of position, which pretty much means like if you're still, whatever energy that thing has, that's the potential energy. Kinetic energy is energy of motion, so if something's moving, it has kinetic energy. Heat is produced from molecular motion, so pretty much like molecules move, which is what heat is. It's literally just the movement of molecules. Mechanical energy is energy from doing work. Uh, atomic/nuclear energy is energy associated with the change in mass of an atom. So when you like add neutrons, that changes the energy up and stuff. Light energy is literally just light waves. Electrical energy is literally just electrical current. That's pretty obvious. And then chemical energy is energy that you can make from chemical change. Right. So, law of conservation or energy of or matter, whatever, right? Pretty much the first definition is that whatever energy you have lost, you have gained it somewhere else. And whatever energy is released somewhere, you have absorbed it somewhere else, right? Pretty much energy, mass, or matter, it cannot be created or destroyed, but it can be converted from one form to another. So, let's say you release heat energy, that heat energy just doesn't go away. It can be converted into like electrical energy, or I don't know, I can't think of anything else, but it can't be created or destroyed, it just changes form. So, yeah. So you have two types of chemical reactions that involve an energy change. You have exothermic, where heat is released. You have endothermic, where heat is absorbed. And these are important to know, pretty much. Yeah, I'm pretty sure, yeah, like every chemical reaction is either exothermic or endothermic, and you have to know the difference between the two of them. Right? So these are the exothermic and endothermic graphs, right? So this one is an exothermic, right? So pretty much in an exothermic reaction, energy is being given off, right? So the products have less heat than the reactants, right? So one way you can tell if it's an exothermic graph, potential energy graph, is if the products have lower heat than the reactants. That's how you tell it, right? Yeah, so this is the potential energy of the reactants, this is the potential energy of the products. This like little hump is to, when you're doing the actual reaction, you need to put energy into the reaction for it to occur in the first place. And then endothermic is the opposite of exothermic, obviously. The reactants have less energy than the products because you are absorbing heat, right? And then again, this hump is when you actually do the reaction, you need to put energy into whatever, right? So, right, and then an increase in potential energy equals a decrease in kinetic energy or temperature, right? And then decrease in potential is an increase in kinetic. I mean, I don't know if you have to know that, but like, I don't remember me having to know that. But then again, I like barely paid attention in chem, so I probably shouldn't be talking. Anyways, so bond energy, right? So I just realized that got cut off, and now that's kind of annoying me like a little bit, tiny bit. Okay, whatever, right? Whatever. So there is energy in bonds, right? So in a chemical reaction, you can break a bond, in which to break a bond, you need to consume energy, because the breaking a bond requires energy. But then when you make a bond, it releases energy. So it's an exothermic. So bond making is exothermic, and then bond breaking is endothermic, right? So yeah, like here, H2 and then O2. So you break the H2, these two H2 bonds and this one O2 bond, right? So this breaking requires energy, but then you reform the bond to create two water, 2H2O, which is which is bond making, which is an exothermic process. So whatever energy they had absorbed from breaking the bonds, it is cancelled out by making the bonds, which goes back to the law of whatever it was called, where pretty much like you can't make or break. Wow, you can't energy cannot be created or destroyed. It just changes form. That's an example of it. Yeah. What is temperature, right? So, temperature, the official definition is the measurement of the average kinetic energy of molecules, right? So, temperature and kinetic energy have a direct relationship. So, um, pretty much if you were to graph like a kinetic energy and a temperature thing, it would have positive slope. I don't know why I'm bringing math into this. I think of math in every ways. Well, but temperature itself is not a form of energy. It's a way of measuring a form of energy. So a way of measuring kinetic energy. That's important to know because I messed that up before. That was really embarrassing. Actually, probably not. I think I'm just the only one who thinks about it. Anyways. Oh, yeah. Yeah, so pretty much, where's my mouse? There it is. So pretty much when temperature increases, the kinetic energy increases, and when temperature decreases, the kinetic energy decreases. Right? And then this is the three ways of measuring energy. You have Fahrenheit, you have Celsius, and you have Kelvin. In science, you're usually gonna you mostly work with Kelvin and Celsius. Nobody uses Fahrenheit except the United States because we're fucking weird for some reason. So you know what? Screw Fahrenheit. But pretty much these are some important temperatures that you kind of need to know. So the boiling point of water is 100 degrees Celsius or 373 Kelvin. The body temperature is 37 degrees Celsius or 310 Kelvin. Or for the average person, I'm probably at like 96 right now. 96 Fahrenheit. I don't know what that is in Celsius. Anyways, the freezing point of water is 0 degrees Celsius or 273 degrees Kelvin. And then the coldest possible temperature that you can create is negative 273 degrees Celsius or 0 Kelvin. And the thing is, with Kelvin temperature, it is always positive. You can never have a negative Kelvin temperature. That is just not possible. Because, So how do you convert between Celsius and Kelvin, right? So pretty much it's on the reference table, on table T. Pretty much you take whatever degrees you have in Kelvin, you add 273. You take whatever degrees you have in Celsius, you add 273, and bam, you got Kelvin. And then you can, manipulate the formula if you need to figure out degrees. So you would subtract 273 on each side. So Celsius is the temperature in Kelvin minus 273. So there's some examples. So do them. Shall wait. Okay, I'm back. So 10 degrees Celsius. Oh, fucking, are you kidding me? The answers aren't here. I have to actually do them? Okay. I have to actually do them. God damn it. I don't feel like doing math right now. This is... Yeah, I'm just homophobic. Okay, well... Yeah, whatever. I'm just gonna assume that you know how to add and subtract numbers because I don't feel like doing them right now. I don't even know where my calculator is. So, next. Anyways. Okay, so on a thermometer there are 2 points that will pretty much always be labeled, which is the boiling point and freezing point, right? And then Celsius and Kelvin are the same size, so pretty much What that means is that if you were to graph them, it would be a proportional relationship with an equal slope throughout. I need to stop saying this in math terms. I'm sorry. I am. Maybe I should just become a math teacher. I think that's my calling. Anyways, but pretty much what that means is that if you increase by 10 degrees Celsius, you increase by 10 degrees Kelvin. So whatever you increase in one thing, you increase in another. Which is why I really like using Celsius and Kelvin, because you don't gotta use the brain. It's very nice. Well, Fahrenheit, being Fahrenheit, likes to be different. So if you increase by 10 degrees Celsius, you increase by 180 degrees Fahrenheit. This is why I hate Fahrenheit. I will go on about this till the day I die. Anyways, Regents question. Okay, woo. So, during an experiment, a Celsius thermometer rises from 10 degrees to 50 degrees. How many kelvins did the temperature rise? Oh, I shall wait. Answer, 40 degrees Kelvin. Why? It doesn't have an explanation. I have to explain this myself. God damn it. Anyways, but pretty much on the Celsius temperature, you increase by 40 degrees Celsius, and because Celsius and Kelvin are equal, pretty much, you have increased by 40 degrees Kelvin. There we go. And then this is just a reminder, exothermic and endothermic stuff, because this wasn't supposed to be done in one day. This is like a multi-day unit thing, but shush. Anyways, heat or energy flow. So energy will always flow from hot heat to cold heat. Hot temperature to cold. I don't know how to word this properly. This is why I barely pass English. Anyways, another Regents question. Woohoo! Okay. Anyways, a hot pack containing chemicals that can be activated to produce heat. A cold pack contains chemicals that feel cold when activated. That is not proper English because there's no parallel. SAT's getting to my brain. Anyways, so pretty much, number 1, based on the energy flow, what type of chemical reaction occurs in the hot pack? Number 2, a cold okay, so let's do number 1. Right, actually, let me just, okay. Based on the energy flow, what type of chemical reaction occurs in the hot pack, right? So the thing is, it produces heat. So we have two things. It could be either an endothermic reaction or an exothermic reaction. But because it's producing heat, it's giving off heat. It's an exothermic reaction, right? And then a cold pack is placed on an injured leg, indicate the direction of the flow of energy between the leg and the cold pack, right? So the direction of flow would be from the leg to the cold pack because on the previous slide it says that temperature or like energy flows from hot to cold, right? So your leg's going to be hotter than the cold pack, so the heat will flow from the leg to the cold pack. Yeah, heat flows from leg to, okay. And then describe how the law of conservation of energy applies to the chemical reaction that occurs in the hot pack. I don't know how to, what's the answer? Okay, so, energy released is energy gained, right? So whatever energy that was lost from the hot pack because it's an exothermic reaction, the leg will absorb that. Yeah. Anyways, or is it, no, because the leg would be cold. Well, whatever. What is heat, right? So heat is a form of energy which is measured in joules or calories. And then the proportion is 1 calorie equals 4.18 joules. The measurement of the amount of heat released or absorbed during a chemical reaction is known as I can't say that, but actually that's how they actually use that to measure how many like calories are in foods and stuff. I'm pretty sure. So that's pretty interesting. Right. So heat. So heat is energy transferred between two objects of different temperature. pretty much heat always flows from hot to cold, and it will continue on flowing until both of the objects are at equal temperature. Equilibrium. Woo! Anyway, specific heat. So every substance has a unique specific heat, and specific heat is how much energy it takes to raise like 1 gram of that object by 1 degree Celsius, right? So water has a specific heat of 4.18 joules gram for every degree Celsius. So pretty much you need 4.18 joules to raise 1 gram by 1 degree Celsius, and that is given on the reference table on table B, right? So the heating and cooling curve, right? So pretty much the heat and cooling curve, they're practically the same graph. It's just that one, the temperature increases as you go by, and the other one, it decreases, but it's the same graph. So as long as you understand it, whatever. It's pretty common sense, right? So pretty much at the lower temperature, you start off as a solid, right? Until you reach a certain point, which is which would be the melting point or the freezing point, right? And then from there, it will turn from solid to liquid, right? And then at this state, right, here the temperature does not change because all the temperature is being absorbed by said object, and my headphone just came out, right? Actually, at this state, the object exists as both a solid and a liquid, right? And then it will remain in that state until a certain temperature, which it then becomes a liquid, right? And then it'll remain in a liquid until it reaches a certain temperature, which is either the boiling or condensing point, in which the object will transform from a liquid to a gas, and then until it reaches a certain point, and then becomes a gas. Then just keeps on staying as a gas as you increase temperature, because yeah. Anyways, finding heat, right? There are 3 heat equations which are all on table T, right? So So the first heat equation, Q equals mc delta T, right? This is used when you have a change in temperature, which is what delta T stands for, change in temperature, right? So so Q is the amount of heat transferred, m would be the mass of whatever you're measuring. C is the specific heat capacity of said object, and then delta T is obviously the change in temperature, right? So what is an example, right? A 2,000 gram mass of H2O and that thing has its temperature raised by 3 degrees Celsius during an exothermic reaction. How much heat is transferred by the heat of reaction? So this is when the Q equals mc delta T equation would come in. So I'll give you some time to do it. I'm going to hope this one actually has the answer, because I don't want to do math right now. Oh yeah, you also might need what's it called? The specific heat capacity, which is on table B. Okay, what's the answer? 25,000 joules. Yeah. It doesn't show how you got it. Well, pretty much the way you got it is that you would take 2,000 multiplied by 3 multiplied by the specific heat capacity, which is I actually don't know what it is off the top of my head. Specific heat capacity of water, 4.18 joules, and then you would multiply all that out to get 25,000. Okay, and then a final temperature problem. Let's see. A 1,000 gram mass of water whose temp was 50 degrees Celsius lost 33,600 joules of heat over a 5-minute period. What was the temperature of water at the end of the 5 minutes? So, you can figure that out. Okay. So to solve for this, it's going to require 2 steps. So the first step is to solve for delta T, right? and then you will just solve for the final temperature, right? So step 1, okay, I guess you're just not gonna show me step 1. I guess so. Okay, well, solve for delta T, right? So the equation is going to be, oh, let me just take my reference table out, because honestly, that would make my life so much easier. Right? So we have, okay, so it's going to be use delta T. So we have Q, which is 33,600 joules, right? And then we have the mass, which is 1,000. We have the specific heat capacity, which is 4.18. And then we're looking for how much it changed by, right? So when you do that and you solve for delta T, you would see that it changed by 8 degrees Celsius, right? You lost 8 degrees Celsius, right? And then you do 50 minus 8, which gives you 42 degrees Celsius. Okay, initial temperature. Okay. A 250 gram mass of water has a temperature of 335 Kelvin and gained 42,000 joules of heat. What was the temperature of the water at the beginning of the experiment? So, pause and, I don't know, figure it out, I guess. Okay, so this one would also require 2 steps, right? So number 1, the same one as before, you will solve for delta T, right? So the equation would be, Q would be 42,000 equals the mass, which is 250. Specific heat is 4.18, and then you solve for delta T, right? Then after you solve for delta T, you solve for initial temperature, right? So the initial temperature is 335, right? So pretty much when you solve for delta T is 4, right? And that's how much it gained. So it's asking what was the temperature of the water before it gained these 4 degrees of Kelvin. Then so you subtract and you get 331 degrees Kelvin. Degrees Kelvin? Or would it just be 331 Kelvin? I'm sure it's just 331 Kelvin. Yeah, anyways. Okay. Copper has a specific heat of 0.39 joules gram Celsius. What is the mass of a piece of copper that undergoes a 25 degrees Celsius temperature change when it absorbs 755 joules of energy? This is pretty much the same thing as the other one, it's just except of using 4.18 as the specific heat, you use 0.39. So, yeah. So the answer is 77 grams. And the way you do this is that you have the Q, which is 755, right? You're looking for the mass, which is your X. You have C, which is 0.39, and then you have the temperature change, which is 25, and then when you rearrange the equation and solve for the mass, you get 77. Okay. So, oops. So pretty much, if the temperature itself does not change, but heat is still transferred, we have 2 different formulas, right? So if you're at the freezing or melting point of a substance, right, you would use heat of fusion. If you're at the boiling point of a substance, you would use heat of vaporization. So this is the heat of fusion of water, and then the heat of vaporization of water, which is also on table B. Table B is so useful. It just gives you the 3 things for water. Physical constants for water. Wow. Anyways, I keep getting distracted. Yeah, but it's the equations and the heat of fusion, whatever, it's all on your reference table. Handy dandy reference table, okay? So how much heat is needed to melt 20 grams of ice at its melting point? So let's do this together. Okay, I hate this PowerPoint so goddamn much. I should have just created my own, but actually I'm really lazy for that. So you know what? I'm just gonna use what my chem teacher used when I had him like a few months ago. Yeah, reference table fell. Ow, back hurts. I'm old. No, I'm not. It's just I don't take care of my body, right? So how would you do this? So you're melting 20 grams of ice, right? So you would be using the Q equals MHF, heat of fusion, right? So you have, so you're solving for Q, the mass is 20 grams, and the heat of fusion of water is 334, right? So when you plug that in a calculator, I'm just gonna use my phone. 20 multiplied by 334. 6,680 joules. And I hope I did that right. I don't know, I can't really check, so I'm just gonna have to rely on myself. How about you do this? Yeah. Okay, so the answer is not. Is this the actual last slide? It is. Okay, well, you know what? Let me just do this then. So, you're at 100 degrees Celsius and you want to vaporize 20 grams of water. So this requires the Q equals mHV heat equation, right? So the mass is 20 grams, and then the heat of fusion is not heat of fusion, heat of vaporization is 2,260 joules per gram, right? So when I plug that in my handy dandy calculator, 20 multiplied by 2260, 45,200. So that's the end of unit 3. Unit 3. Yeah. Hope chemistry isn't going to kill you. I don't know. I don't know what else. I don't know how to end it. I never know how to end or start these videos. I just kind of just talk. And I just sound like an idiot. Yeah. Anyways, okay. Bye bye.